Hello and welcome to Toddcast number 4. I'm going on the assumption that you have been watching the previous ones, so hopefully that's true. I'm going to continue with geometrical structures and go into the cause behind them, hybridization. And so just a few things to make sure we have understood. The steric number represents the number of electron pairs around a central atom. So it's the bonds plus the electron pairs. You know the steric number. If you know the steric number, you can get the hybridization. They go hand in hand. So the number of atomic orbitals in your hybrid has to equal your steric number. So for instance, if we call something an sp hybrid, there's one s and one p in that, so that would be 2, it's a steric number of 2. If you have an sp2, then there's one S and two P's. So S plus two P's be 3. So steric number of 3. And then sp3 and S and 3 P's for a steric number of 4. So if you get that down pat, you can hear me say hybridization and steric number kind of interchangeably. They represent number of atomic orbitals in the hybrid must match a steric number. So geometrical structures want to pick up right where we left off at the tail end of Toddcast 3. And that is there's going to be a bond forming here and here, bond here and bond here. And because it has a steric number of 1, 2, 3, 3 atoms attached and no lone pair in the central atom, 3 would be sp2 hybridization. That's what we'll get to. And if there's 3 things, it's trigonal planar. So it's going to be our structure. So the bonds will come together. Let me erase my mess and tell you that you have a bond there, you have a bond there, and 2 bonds there. So that's what your structure is going to look like. I want to emphasize it is trigonal planar and has a steric number of 3. 1, 2, 3 things attached, 3 electron-rich groups. Okay, so lone pairs and atoms is your steric number. Okay, then I'm also going to revisit ammonia, which we did in a previous lecture. That's going to have, again, one bond here and here, one bond here and here, one bond here and here. They come together. So you have a bonding pair, bonding pair, bonding pair, and a lone pair in the nitrogen. So nitrogen will have a steric number of 4 because it has an H, an H, an H, and a lone pair. So when it has a steric number of 4, it can be tetrahedral for its electronic geometry. Okay, so quick review to get into the crux of things. So I want to emphasize from this geometrical structure that we just studied, want to emphasize the hybridization. I want to make one note. You're going to see these dashed lines and wedge lines. So this H is coming out. These represent going back. The bond angle between anything in a tetrahedral, 109.5 is my guess. If you learned from Vesper when you took GChem, lone pairs offer more repulsion because electrons are closer to the structure than they are in a bonding pair. So it's going to push it down. So it ends up, it's going to be probably around 107 degrees, but it's in the ballpark. So you start with an estimate of 109.5 and make whatever adjustments. Okay, hybridization. So hybridization, a hybrid, if you ever heard this term, is a mixture of 2 things. Hybrid plant, 2 plants that have been fused together to form some mixture. Hybrid animal, I believe the donkey is a perfect example, or I may have this wrong, but a horse, somehow a horse, donkey, and a mule, you can put 2 animals together and get the 3rd animal. And then cars, they have an electric motor and they have a combustion engine, both if it's hybrid car. So hybrid simply means we've mixed multiple things together. So all those examples had 2. So we're going to mix 2 types of orbitals, but if you recall, there is only one 2s, but there are 1, 2, 3 2p's. So how we mix them together will depend. So I'm going to start with sp3, which simply means I'm going to take the s, a p, and a p. The 2 is not necessary. You can have hybridization in atoms that aren't carbon, but because we deal with so much carbon, nitrogen, and oxygen, I'm just going to get in the habit of using 2p and 2s. And so these are your orbital levels. You fill S before P, so it's lower in energy. Energy must be conserved. So when we mix everything together, if you have 3 at high energy, 1 at low energy, then the average of all three is going to be up closer to here. So these are going to go down a little to make up for this one going up a lot. So the hybrids are going to be here. So notice they're higher from the S than they are from the P because they're an average energy of all these in a mixture. So I'm mixing 1, 2, 3 P's in an S. We're going to call them sp3s. No longer do we have a designation of 2. And the reason that's true is because in atoms, we have shells. First shell, second shell, third shell we worry about. For bonding, we only care about shared electrons. So it's going to be the valence shell, and any valence shell can share. So it's not as important to put the number here. We just know that automatically you're hybridizing valence electrons. So you've mixed some P's from the valence shell with an S in the valence shell to get an sp3. Okay, for carbon, one electron spin up, next electron spin down, and you fill across, up, down, but it only has 4, 2s2, 2p2. So up, down, up, and up. So there are my electrons. These electrons are now going to occupy, which means we just went from a picture that looks something like this, carbon with a lone pair and 2 electrons, to tell you that's not the way it works. The way it actually works is carbon with electron in one sp, electron in another sp. That's an orbital going back, has one electron in there, and then coming out that's bolted, one electron. So really, this picture, because we're dealing with molecules, not atoms, the atomic picture, atomic orbitals, are useless to me. Everything I'm going to worry about in OChem, because I worry about molecules, is going to be the hybrid. So sp3s not only mix together equal in energy, but they space themselves out so they can form, if I did a line like that, angle would be 109.5 degrees. Okay, so tetrahedral in shape when it's sp3. But sp3 isn't the only one we get. We can sometimes mix, in this case, an S with only 2 of the P's. So I might mix this one and this one, but this one is going to stay. So that means these two and this one have to be of average energy. So it might be really subtle, but this went down, let's say a third of the way, this, or 1/4, this one up 3/4. This went down 1/3, this one goes up 2/3. So this energy set and this energy set, these are slightly lower, meaning sp2 are ever so slightly more stable than sp3, which we're going to get into a whole bunch of things down the road, how to predict reactivity because of that. But hybridization, again, you have to average the energy of the 3 orbitals we're mixing. So you're going to have sp3 up here sp2. Notice that there's 4 sp3s because I'm mixing 4 orbitals. There are only 3 sp2s because I'm mixing 3 orbitals, and I'm leaving one of the 2 p's. And then also just to emphasize, these are lower than they were for the sp3, again, because you're averaging only 2 high and 1 low. Okay, and then I have to make sure the 2p comes across. So that's all fine, but must also have a 2p orbital that was unaffected. So I move my 2p over here, 1 electron in it, and the 2p level. So these are your hybrids. This is your same electron that it was before. And that's going to form what's known as a pi bond eventually. Okay, so we're rolling. So I have the rules. When I mix a py with a px and a pz, this is supposed to represent going into and out of the plane. Didn't come out very pretty. But like I said, when you mix these 4 together, you get 4, number going in must equal number going out. They're going to be at different angles. So if I put an angle here, if I could put those points together, it'd be 109.5. 109.5 if I put these things side by side, but 4 in, 4 out. If I put a PPP and an S, then I get PPPS, 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 and PPPS. So sp3 when you mix. sp2, we mix, let's say a px and a py. It doesn't matter which 2 we mix. Add in an S, and you get sp2, sp2, and sp2. These are all trigonal planar, so if I drew my axis here and here, they would be on axis, slightly off axis, slightly off axis. Okay, and then I omitted in the energy diagram the SP. So 2 go in, 2 go out, 1 point's left, 1 point's right. That's going to be one of my easier ones. Okay, have to know that concept of sp3 means an spp, so you've mixed together 4 atomic orbitals to make 4 sp3 hybrids. spp, sp2, you mix an sp and a p, so 3, so you get 3 sp2s, and sp, you mix an s and a p. Okay, here's what really matters. Here's the take-home message. So you have these things from before. Keep in mind the steric number can tell you the hybridization. Steric number of 2, sp. Steric number of 3, sp2. Steric number of 4, sp3. And then you also can note that your structures, your shapes are going to depend on your hybridization. So when we have an sp3, because it has 3 parts p to 1 part s, it's going to be a little bit longer than an sp2. It's really subtle. But if you can see, if I drew a line right here, which I will, I'm going to compare the length of the different hybrids. So more P character, the longer it is. Medium amount of P character is going to be medium, mostly like half and half. More S character is going to be shorter. So notice the length from one end of the lobe to one end of the lobe is very long. If I bring these lines straight down, you'll notice that it's the gap, so I got to move it over a little bit. So it ends up, this one is medium in length. And then finally for this one over here, this one's going to shorten up. That shortens up a little bit. So this one comes in, that one comes in. And so your hybrid length, this is absolutely imperative you know this. So sp3 orbitals are longer than sp2, which are longer than sp. Meaning if you form a bond using long orbitals, it'll be a longer bond. Use shorter orbitals to make a bond, you get a shorter bond. Generally speaking, shorter bond means electrons are closer to nucleus. Closer to nucleus, they're feeling bigger plus charges, they're held more tightly. So shorter bonds are in general stronger than longer bonds. So that's where hybridization is going to matter. It's going to help us predict. So again, if you make a longer bond, the atoms are really far apart, so they're not held together as tightly. So longer bond or longer orbitals result in longer bonds, which are weaker bonds. Shorter orbitals result in shorter bonds and therefore stronger bonds. Okay. Can I add one more piece of the puzzle? This is kind of a cutesy thing, but the acidity. This is going to be sort of weird, so I'm going to draw a picture here to explain it. Acidity is ability to give up an H plus. Let's say it's a short one compared to a really long one. So on average, the 2 electrons are going to be a little closer to carbon than they are hydrogen because it's more electronegative. So if this bond breaks, H is going to get a plus and carbon is going to get the lone pair. In the case of a shorter bond, the lone pair is on average closer to carbon. So it's already where it needs to finish. So it's going to be easier for this lone pair to just get really close to carbon because it starts so close to carbon, meaning this can easily give off an H plus and a C minus. So it can easily lose that H and turn into C minus and H plus. This one, not as much. And easily is a relative term, more easily than the longer one. So when I say acidic, I really should be saying acidic. So there must be a reason why I'm misspelling. Could be my educational background. That's often the case. But in this case, that's not what it is. In this case, it is because I want to emphasize something called S character. If you just do a straight average, if it's 1 S and 3 Ps, then 3 out of 4 are Ps, 1 out of 4 are S. So it's 1/4 S, or they call it 25% S character, meaning the hybrid is made up of 25% S. If I have sp2, 1 S with 2 Ps, it's 1/3 S, which is 33% S character, and sp, half and half is 50%. So the term S character refers to what percentage in the hybrid is due to the S. So from sp3 with 25 all the way up to sp with 50. As I go from sp3 to sp2 to sp, the amount of S character increases. And when S character goes up, everything beginning with an S also goes up. So if you have more S character, then you have more S stuff. You are S shorter, S stronger, and acidic. So really good way to remember that. The more S character, the shorter, stronger, and more acidic something is. So we'll call this mnemonic number 1. Easy way to remember this, more S character. SP has more percent S in its component, or more S component in its hybrid. So more S, more strong, more short, more acidic. So now I'm speaking like I spell. So shorter, stronger, more acidic. Okay, so if I consider C3 to CH3, that's a case of SP3 to SP3, CH2 to CH2. I'm going to have a double bond in there. I'm going to draw it in a second. CH to CH. So if I have 1, 2, 3 H's in a carbon, that's steric number 4, so SP3. 3 H's in this other carbon, so steric number 4, so SP3. 2 H's in this other carbon, so 2, so SP2. 2 H's in that carbon, SP2. And then finally, CH, so an H in a carbon, just steric number 2, so SP. It ends up, this will be your longer bond, this will be your shorter bond, this will be your middle bond. And the only way that can happen is if I have a double bond, so carbon shares 2 bonds, and then a triple bond. So you're going to note that triple bonds will generally go with sp hybridization. We're dealing with carbon, nitrogen, and oxygen. It has to go with sp hybridization. Double bonds will go with sp2. Single bonds would go with sp3. We'll get more into that in a very near future Toddcast. Okay, so determine the shape around the central atom. Steric number predicts the structure and it predicts the hybridization. So we're going to use that together. So sp, sp2, sp3, some more S character, steric number 4, medium amount of S character, steric number 3, most S character, sp, and steric number 2. Hopefully I said that right. So there's my steric number. Bond angle, when it has steric number 2, when it's said to be linear, steric number 3, trigonal planar, so bond angle 120, tetrahedral 109.5. Again, these will deviate once you put other atoms in there, but just note that you're responsible for knowing linear should be 180, trigonal planar should be roughly 120, depending on how electrons spread. Tetrahedral should be 109.5. Your shape, don't know because I don't know what the central atom is, but probably going to be linear in this case. This one, trigonal planar or bent, depending on how many ligands you have, and tetrahedral, trigonal pyramidal, bent, depending again on how many atoms. So how many within the steric number are due to atoms that are attached. So hybridization shape table, putting it all together. Coordination number, that is just the number of atoms attached, not your lone pairs. So if you have coordination number of 2 things attached, and 0 lone pairs, your steric number is 2, the sum of these two. SP hybridization, linear 180. Good example is CO2. It's a linear structure. So note that it has 2 atoms attached, and it is linear in nature. If you have a coordination number of 3 atoms attached, no lone pairs, and 3 plus 0 is 3, so steric number 3, so SPP or SP2. When it's SP2, it's going to have a bond angle 120. The geometry, the actual electronic geometry, how electrons spread themselves, they do it in trigonal planar fashion. Because there is nothing else attached, then it's going to also be a trigonal planar structure. So there's no lone pairs. So there's no lone pairs. The shape and electronic geometry are identical. So BF3, trigonal planar molecule. Now I'm going to get a little more advanced. If I have 2 atoms attached plus 1 lone pair, so 2 plus 1, steric number 3, so sp3, so trigonal planar electronic geometry, 120 angle. This is where we're going to have the angle probably end up being a little bit less because of lone pair repulsion, but the structure ends up being bent. So if I draw this out, this angle here to here, I predict 120 because this lone pair repels. It's going to push those atoms away a little bit. Angle is probably going to be around 119, 118 or so. Okay, so we're seeing a trend here. If I have 4 atoms attached to no lone pairs, 4 plus 0 is 4, so steric number 4, sp3. Tetrahedral, no lone pairs, so shape and electron geometry are the same. 109.5, and CH4 is my typical example. If I have 3 plus 1, So that's going to be a steric number 4. So sp3, 4 would be spp, spp, hopefully I said it right, sp3, so tetrahedral, but because I have a lone pair, that is a case now where the geometry, electron geometry, doesn't match the shape. First predicted angle, 109.5, lone pair is going to cause it go down, like mentioned earlier, to probably around 107. And we don't care lone pairs in the shape, so the shape is going to be, if I drew this out, a pyramid with a trigonal or triangle as a base, so trigonal pyramidal. Okay, so let's see the pattern we have going. Steric number of 2, SP. Steric number of 3, SP2. Steric number of 4, so I guess I must have one more coming up. Let's see what I did. I did a 2 and a 0, and I could have done a 1 and 1, just didn't toss it in there. 3 and 0, 2 and 1, could have probably done a 1 and 2, didn't. 4 and 0, 3 and 1, so probably going for 2 and 2. So there we go. 2 atoms attached, 2 lone pairs, so 2 plus 2, 4, steric number 4. SPPP, tetrahedral, because SP3, 109.5, because it's SP3. Water is your typical example. It's said to be bent because, again, we only consider the atoms. 109.5 is a good first guess, but because I have 2 lone pairs repelling it, goes down to about 104.5 for the bonding. So SP 180, SP2s 120, SP3s 109.5 for first guess. No lone pairs, shape and geometry are the same. Notice that SP, steric number 2, linear, SP2, steric number 3, trigonal planar, SP3, steric number 4, tetrahedral. There's a pattern. It's just, you just compile this information and it falls in place nicely. So the structures are, again, linear, trigonal planar for BF3, bent for SO2, CH4 is tetrahedral, the NH3 is trigonal pyramidal, and last but not least, water is bent. Have to know your structure. So this review, I'm going pretty quick through this one. You have to go back and methodically go through these. You have to know all 6 of these as a reflex, not a thought. You can't process it. You have to just know it. Okay, so 3D structures. Carbon dioxide is linear because it has 2 things attached and no lone pair. Steric number of 2, SP, so SP hybridized is linear. 1, 2, 3, as we mentioned, no lone pair, so SPP, so SP2 hybridization and trigonal planar. 1, 2, 3, 4, so steric number 4, SP3 hybridized, so tetrahedral geometry. Ammonia, so 1, 2, 3 plus a lone pair, so steric number of 4, SP3 hybridized. This is a case where the electronic geometry is tetrahedral, but the shape is actually trigonal pyramidal. And then tossing kind of a monkey wrench in the crankshaft, 1, 2, 3, 4, 5, 6. So bring back a little bit of GChem. A steric number of 6 would be S, P, 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 all out of S and P, so I got to go to D. So we end up with an SP3D2 or D2SP3, depending on how you state it. So central atom has to have 6. So that'd be its hybridization. Octahedral, if you happen to remember that. Not important for this class necessarily, but just part of your review, 3D structures. Important, 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 important. Used to be important when you took general chemistry. So BH3, want to emphasize, I've drawn an orbital here. So we still have an empty p orbital is what we're going to call it. You're going to hear me use this phrase from time to time. Empty p because boron only had 3 electrons, so it can only hybridize with 3. But it can still react. It still can pick up some sort of electrons, and gaining electrons will make it negative, but note that it is trigonal planar. CH4, sp3 hybridized and tetrahedral. The lone pair is here for nitrogen, although it can flip back and forth. So I drew the lone pair on the top. It could also be on bottom. And then water, same sort of picture. So this is the same thing we just did. I'm using the same molecules over and over, but to give you the three-dimensional picture that I want you to have in your head. So I want you to instantly see CH4, sp3 hybridized, steric number 4, tetrahedral. Just those things have to be bam, 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 bam. Okay, big picture, giant table, everything we just did all over again. So coordination number 2, no lone pairs. That means that has steric number 2, sp is 180. So CO2 is our example. When you have coordination number 2 and one lone pair, like we did, then you end up with a bent shape. When you have coordination number 2 and two lone pairs, so 2 plus 2, 4, steric number 4, sp3 hybridized, shape is bent, bond angle is going to be a little less than 109.5. When you have 3 with no lone pairs, 3 plus 0 is 3, steric number 3, so sp2, 120, trigonal planar. When you have one lone pair plus 3 things attached, coordination number 3 plus 1, steric number 4, spp, sp3. And then when you have 4 with no lone pairs, steric number 4, tetrahedral, that's your shape. So that one was CH4. So again, this is the same thing. I'm doing the same thing over and over, but now in possibly a prettier picture. So want you to know this information. That's why it's on 3 straight slides over and over and over. Repetition, so it went slow, medium, and went really fast this time. But once you feel it's in a good spot, this might be the page you want to like print out or work from on your notes. Okay. So last of the summaries then. So molecular and structural formulas. So note that we've started this as writing C2H6O. I kind of need to know how that works. And then CH2, CH3OH, or CH3CH2OH, excuse me. So the Lewis structure would be carbon-carbon with an OH at the end. So start with carbon 4 bonds each, O with valence lone paired, and add the H's. But the 3D structure, everything is steric number 4, 4, and 4. So everything starts out with tetrahedral electronic geometry. So up and in the plane, bond angle 109.5-ish. And then in and out, next carbon, inverted, same thing, 2 in the plane, in and out for the other ones. O with a lone pair. We have dimethylamine, C2H7N, which would be drawn in this way with a CH3, NH, and CH3. So we did this example already, but now everything is, again, 4, steric number 4, steric number 4, so everything's sp3 and therefore tetrahedral. So I have this one, which is kind of in the plane with this one, but I'm drawing it in that way to emphasize these carbons are coming out and that H is going back. So central atom has trigonal pyramidal alignment, and then each of the carbons has an H in front, H in back, and an H in the plane. If we have a ion, so basically if I take this structure right here and somehow, some way can lose an H up top, that lone pair is going to become a bond. And that's what you end up with here. Carbon has 1, 2, 3, 4 bonds at set, but oxygen has 1, 2, 3, and 1 lone pair. So it normally has 6. Here it only has 5. 6 minus 5 plus 1. Notice the shape changed. sp3, because it has a steric number of 4, but this one became sp2 because it has a steric number of 3. So this is now trigonal planar. Imperative to know that when you lose an H, where you end up losing it, or add an H, or whatever you do, you end up changing steric numbers, so the structure changes. So this is foreshadowing. This page is a little ahead of our time. If you understand it, great. We'll get there in time. But note that this Lewis structure doesn't tell me what's going on, but this does. So when I went from tetrahedral to trigonal planar, the molecule changed enough, and by changing its shape and taking on a plus charge, it just made itself more reactive. So protonated is going to be more reactive than deprotonated. Or I guess what I should say is positive in this case is going to be more reactive than neutral. Okay, a lot of stuff going on. This was a pretty impacted one. Again, each Toddcast is going to get a little more impacted as we go. Hopefully this went well. and I will see you at the next one, or won't see you and you won't see me, but words will happen and you'll hear it. So have an absolutely wonderful day and see you at the next podcast. Bye.